there.
All right, so this is a version of a talk I gave at Ocean Sciences as well as in Hamburg and in Grenoble. So if any of y'all were there, there'll be some repeats. And this is from Bob, Alistair, and I, and a lot of it is taken from a manuscript that is in review at James, talking about the method of how we solve the equations in MOM6, thinking of it more of a fluid mechanic perspective than a numerical perspective. So I hope that I can convey some of the sort of higher level conceptual understanding of what's going on with MOM6 to those that may want to understand that and not really able to dive into the numerical details, kind of, which is what I found myself in a few years ago. Next slide. So there's some key points to the talk, and I want to remind people of some of the motivation for doing what we do in MOM6. And one of the big motivations stems back from a 20-year-old problem, namely spurious dipycnal mixing, that can be exacerbated in Z-like vertical coordinate models or sigma coordinate models or models that don't have sort of a quasi-isopycnal nature to it. And the dynamical core formulation that I'm going to talk about is what we call vertical Lagrangian remapping. And a lot of people call it ALE for arbitrary Lagrangian Eulerian, and I'd like to make a distinction here, and I'll try to highlight that as we go along. And I'm going to offer a conjecture, and it's nothing proven in this work, but it is something that we're hoping is going to be proven in the community over the next decade, is that the vertical Lagrangian remapping provides an appropriate hybrid vertical coordinate framework to perhaps even optimal framework to solve the spurious mixing problem in a way that allows us to also solve the global ocean circulation problem numerically. You can solve the spurious mixing problem for the most part by going 100% isopycnal, but you compromise your ability to do the coastal problem and the high latitude problem when you go isopycnal 100%. Whereas a hybrid approach that's implemented through vertical Lagrangian remapping, we think is a good framework to do both. Okay, next slide. Next slide. Next slide. Yeah, I'm going pretty fast here. Anyway, the mixing problem. Now this is rudiments for many people, but I'm hoping that it will be new to some. So we're basically in a point in the community that we are able to make physical statements about mixing in the ocean. This is a contrast to maybe 20 years ago where there was really lots of unknowns about what were the physical mechanism for mixing. I can't say that we 100% understand everything, but this picture here from a review article from Jennifer McKinnon, which is the result of a climate process team that finished a few years ago, is exemplary of a lot of the physical processes that we have a grip on now, and we have some rudiment parameterizations of these processes. There's more work that's going on with a big center of excellence in Germany, also looking at similar questions. And we really are at the point where the physics is going to be compromised in a way that's not good if we have spurious mixing coming from the numerics that can sometimes swamp the physics. So we need to be mindful of spurious mixing. Next slide. So just to frame the problem, you have, and it's coming through advection. That's what I'm talking about here. There may be other sources of spurious mixing, but I'm mostly focusing on the advection operator. So equation one is a sort of generalized advection operator in a model, which is, something exact. Now, what is exact? Well, let's just call it something exact that you could do if you were infinitely resolved and numerics were perfect. Plus you have an error term that's due to truncation errors, and that truncation error is dependent on the implementation of your numerical advection operator. So that truncation error in some cases can be as big as the physical operator, the J vector, in number equation 2, and that then compromises your physical simulation. So it's a key concern for climate in particular because the spurious mixing can accumulate over long periods of time and lead to degradation of your thermocline, picocline, for example. It can degrade your tracer concentration in a way that's just not physically desirable. And it's reduced when you use a quasi-isopycnal vertical coordinate. because errors stopped at the interface, actually using really, yeah. But again, as I said earlier, an isopycnal approach, 100% isopycnal is difficult, if not impossible, to do the world ocean circulation. So we're looking for something different. Next slide. So let's, this slide, I'm gonna skip through a couple of slides really quick. There's methods to diagnose the spurious mixing, going back to this paper I wrote with Bob and Ron Pakinowski 20 years ago. And just diagnose the magnitude of the mixings that we're getting with certain operators. And it can be upwards of 10 times larger, maybe even larger in some cases, 10 times larger than what you would want from a physical sort of background 10 to the minus 5 meters square per second mixing level. So what we have found in some of the studies that came subsequent to that, in particular a paper by Illichak et al. 2012, is that there is a real important need to combine your grid Reynolds number, namely the friction you use or the viscosity you use in a model, and the spurious mixing. So there's a direct relation between the two. And it's easy to understand that, to sort of take the extreme case where you have little, if no, horizontal viscosity, and your model is just rip-roaring with strong currents, but you're gonna get a lot of grid noise. And when you allow for grid noise, that is acted upon, that velocity field that's noisy is going to be taken by your advection operator. And if you have a flux corrected advection operator or a monotonic advection scheme, that scheme is going to introduce mixing to smooth out the advection operator to keep you from producing extrema. And of course, if you have an operator that's linear, that's not flux corrected or flux limited, then you're going to get a lot of dispersion error that creates negative and positive mixing, kind of like the old days of second order center difference advection, where you get huge extrema of water masses. So there is a real need in any of these simulations to be mindful of the grid Reynolds number. You can't, there's no free lunch effectively. You can't just run with reduced numerical friction. Even though the model is stable, it's not blowing up, it still may be producing lots of grid noise. Okay, so next slide. So subsequent to that 2000 paper, there's a whole cottage industry of methods to diagnose spurious mixing. It's not really easy to do, especially when you have a nonlinear equation of state. And so there are lots of different ideas out there. And next slide. Next slide. Yeah, so just the general points. I'm sorry, previous slide. Spurious mixing, diagnosing spurious mixing is useful for understanding its character, but it is insufficient to remove the problem. Higher order numerics help, namely there's a paper by Hill et al. In 2012 where they looked at the Prather advection scheme, which they claim they solved the spurious mixing problem with using the Prather advection scheme. And they did perhaps solve it in a flat bottom numerical model without any real without realistic forcing going on with a linear equation of state. But you still need, when you add passive tracers like biology, we have found that you need to have flux limiters. And when you add flux limiters to the Prather scheme, it reduces the accuracy of that scheme down to something like a piecewise parabolic method, limited piecewise parabolic method. So that's not the solution that we have found. Really, you have to maintain a modest grid Reynolds number and use a good advection scheme in addition. And the problem arises from advection both in the vertical and the horizontal. There's a paper by Gibson et al. That decomposed in MOM6 the contribution to spurious mixing from the vertical remapping as opposed to in contrast to the horizontal advection along layers. So anyway, let's skip to the next slide, because that's our more motivation, just to summarize the state of the science of the spurious mixing. So we'll talk about the next slide, the vertical Lagrangian remapping. So we're going to focus on the vertical, and that's really been the theme of a lot of the work that GFDL has done the last, really, since Hallberg came to GFDL in the 90s, really focusing on the vertical and the physics as well. And isopycnal models have their role in the climate problem. But again, we have found that there are limitations to that. We built a climate model with the gold isopycna model, and it was a very respectable model. But they have their problems in high latitude unstratified regions, which argue for hybrid. And the vertical arbitrary Lagrangian Eulerian method, the ALE method, which includes a special case of vertical Lagrangian remapping, is the strategy we've taken. So let's propose a terminology, and that's what we use in our paper that's being reviewed right now. Quasi-Eulerian is something like what we have in MIT GCM, MOM5, ROMs, where you solve the equations very similar to almost like what Kirk Bryan did in the late 60s, but you allow for the vertical coordinate to go up and down. But they're Eulerian. It's an Eulerian method. Vertical arbitrary Lagrangian Eulerian is you can implement that with or without remapping. Now the NEMO code and the Impasse Ocean code call themselves ALE, but they don't do remapping. Whereas HICOM and MOM6 is a fully Lagrangian approach in the vertical, and they have to be fully Lagrangian, you have to remap, because at some point your coordinate is going to lose its ability to simulate the flow, because the coordinate is going to drift. And just like any Lagrangian approach, you're following particles. At some point, you got to renormalize or reinitialize your coordinate in order to maintain the integrity of your numerical simulation. That's done by a remapping. In the ocean, we do this in the vertical only. Whereas in some communities, like the bomb simulators at Los Alamos, they do a full 3D Eulerian Lagrangian approach, well, Lagrangian Eulerian approach, or full 3D Lagrangian approach. And so they have a much more complicated regridding, remapping problem than we do. Okay, next slide. So let's start from a fluid mechanic perspective, a finite volume or weak formulation. And just recall, if you've never seen this, this is the name. It's called the Leibniz-Reynolds transport theorem. And just focus on the tracers. It's easier to think about. The first equation on the left top is a time derivative of the tracer mass over some region of fluid. And this kidney-shaped region on the right is an example. And that changes, that time tendency is a function of the advection through the boundary, which is the first term, and the fusion at the boundary, which is the second term, the J term. And that advection term is a relative advection. There's a velocity v of the fluid itself and a velocity v super b of the boundary of that region. And you take the relative velocity of the two to give you the amount of advection through that domain. Okay? And the momentum equation has a similar expression where you have body forces and contact forces. So the discrete equations follow by specializing this region R to a model grid cell. It could be a fixed cell like we did in the old days with top and bottom and sides all fixed in time like we did in the Z models. We can have the quasi-Eulerian models where the top and bottom can go up and down in a specified way. Or we can have different, more general ways of doing it like we have in the Lagrangian approaches. Models typically formulate the scalar prognostic budgets for extensive quantities like heat and salt, not temperature and salinity. Okay, so you may see me in other contexts being a little bit anal about this distinction, and I think it's important to remember that we're solving a heat equation and a salt equation, not a temperature equation and a salinity equation. That makes all the difference in the world. Well, it makes a big difference when you're talking about diagnosing budgets. And a lot of what I do now is analysis of these simulations, and talking about budget analysis is a big deal. However, when we're doing the velocity or the momentum, we often reformulate things in terms of vector invariant velocity equations for various reasons, such as Sojourning energy entropy is a favorite numerical method that some people like. So I'm not going to talk about the momentum equation or the velocity equation in this presentation, but it is a distinction that is important to keep in mind if you're talking about diagnosing those terms. So advection, again, refers to the transfer of the fluid relative to the grid. A fully Lagrangian method has zero advection, okay? But again, fully Lagrangian at some point is going to fall flat on its face because the grid is going to evolve so far that you're losing your ability to simulate the flow. So you have a turbulent flow or you just have an unstratified region, you need to regrid at some point. And fully Lagrangian has all motion leading to advection. All motion relative to a fixed grid is advection. So this is nothing more than just basic fluid mechanics, but it is translated into a numerical method in the way we do things in these vertical Lagrangian approaches. Next slide. So this is one of my favorite figures, which I think a lot of people said is a good intuition for the arbitrary Lagrangian Eulerian method. So it's a little more specialized than the previous kidney-shaped figure that we had. In this one now, we have three figures, left, middle, and right. The left figure, you say you have a square region of fluid, okay? And now let's put into that region of fluid a grid line. And let's paint a blue and a yellow stripe in that grid, okay? So that's the initial fluid region and the initial grid, all right? Now let's let that fluid evolve over some small but non-zero time difference, okay? As that fluid evolves, the grid may or may not evolve with the fluid. In this particular example, the grid is evolving with the fluid, and the fluid itself, the yellow and the blue stripes, are evolving. And as I've drawn this here, they're evolving together, okay? But they need not evolve together. You may have the fluid evolve a little bit more or a little bit less in different ways than the grid itself. That's a choice of the model developer or the model user. I've drawn it here as if the grid is evolving as a Lagrangian grid. The next step is an optional regrid. Okay, if your grid evolves in a Lagrangian way, as I've said a few times, you eventually have to regrid, okay? And as you regrid, your grid in this case moves back to some reinitialized position, and you see that the state of the fluid is distinct now from the grid, all right? And so, however, your fluid needs to be known, needs to be placed back on the grid. You need to have that grid has to carry information about the fluid. And so that's the remap step. The remap step is not moving the fluid itself, it's just moving where you know the fluid exists, the points where you have the information about the fluid, okay? So I just, let's see if I'm gonna read here, if there's anything new. Step one, if the grid moves with the flow, it's a Lagrangian step. Non-Lagrangian grid motion is also considered by certain Ale approaches, such as what we have in Impasse and NEMO. Step two, the regrid and remap step, they come together. They ideally, they do not alter the ocean state, but of course, due to numerical truncation, you will have some altering of that state. The remap step operationally equals to advection. It's a transport relative to the grid. Remember that sort of mantra that I mentioned earlier. What advection is, it's transport relative to a grid. Ocean models restrict their moving meshes to be just in the vertical and formulate the equation using generalized vertical coordinates. Okay, next slide. So we distinguish the solution methods. Here's a typical grid cell in an ocean model that's sitting away from the boundaries. So we have, I'm using the symbol sigma for the coordinate grids. And we have outward normals, and X, Y, and Z is oriented as shown. If the lateral boundaries and typically the lateral boundaries in ocean models are fixed, we don't have fully moving grids in most ocean models, at least the ones that we're talking about here. And so the lateral boundaries where flow moves relative to that fixed boundary, that's horizontal advection, just like familiar horizontal advection. Rigid lid Z models have the vertical fixed, and they're also flat, well, effectively flat. And so any vertical motion is a vertical advection in these models. Likewise, for free surface models, vertical advection is through the interior vertical cell faces, and the top of the ocean is the one that moves. We have analytically specified coordinates such as Z star or sigma coordinate models, where you effectively filter out the barotropic motions in these models. Isopycnal layers are determined by layers that are interior layers that follow the fluid itself. And more general ALE allows for the top and bottom interfaces to be arbitrary. So this is kind of a categorization of the different methods based on just looking at how we specify the grid motion itself, the grid being the top and bottom interface of this cell. In an ocean model, again, it's just the top and bottom interface that is moving in time. Next slide. Let's skip this slide. So now we specialize a little bit more to show a typical flavor of a vertical Lagrangian remap method. And this is a depiction of a vertical and horizontal layering of the ocean according to a grid. And we have, again, an initial state and various subsequent states. So let's talk through this figure here. This is also a very, hopefully, intuitive figure for what's going on in MOM6 and HICOM. So we have an initial state on the left with everything horizontal, and the grid lines are horizontal, and the colored lines are representing the fluid itself. And in this case, they represent a tracer or like density, for example, or temperature. So the next line is an evolution of that ocean state according to, say, a wave that goes through the fluid itself. Say it's an internal gravity wave that moves the interfaces of the isopycnals up and down. And this first step of the algorithm, the grid follows the motion of the fluid, okay? We've already talked through this, but this is now getting more specific into the MOM vertical isopycnal approach, vertical Lagrangian approach. The next step, we regrid, okay? Now we don't have to regrid every time step, but in this particular example, let's just assume this is the regrid step. All right, so we're redefining the grid. The dashed lines now are the ocean state, and the solid line is the grid, the new grid. And now the fourth panel shows a remapping of the state onto the horizontal lines. Okay, we still see the dashed lines for the previous grid, but as we see, I don't know if you can tell, you can probably tell going to the final state where we remove all the old grid lines, you can see that there's a bit of diffusion in the process of that regrid. Okay, and so because we have a finite vertical representation, finite vertical grid, and so there is some diffusion in that remapping step. All right, and of course, a lot of people ask, well, why do you know, there's a lot of diffusion there. Why don't you do something better? Well, of course, this is just a pedagogical example. If you had fluid mechanics where it was just pure isopycnal flow, then your vertical Lagrangian model would you would choose isopycnals as your vertical coordinate instead of a z coordinate as we have here. But this is just the example that I wanted to show that allows for you to see the different steps in the vertical Lagrangian approach, and hopefully gives you a sense for why there is some mixing associated with that remap step. So let's see, did I say everything along here? Again, just to give you some context, the impasse people at Los Alamos and NEMO has what they call a Z tilde coordinate. They don't do the remap step. Their grid evolves in a way that's somewhat similar to this particular example here, where they follow gravity waves effectively, but they always damp their grid back to something that's quasi-horizontal so that they don't lose grid resolution enough that they need to remap or regrid, okay? So they sort of constrain the amount that their grid can move in a way that allows them to avoid the regrid remap step, which is, you know, that regrid remap step requires a lot of technology, and it's an important step to get the numerics right. And it's something that evolving a model such as impasse and NEMO from Z-like models to something more general, it's a totally rational approach to say, well, let's do something in between the fully Lagrangian remap. Next slide. So again, where is advection? Where is the advection across coordinate surface? That is, again, in the remap step. It's the movement of your representation of the grid of a state relative to the grid, okay? The remap step, you are changing how you're representing your state from one grid to another. And so you're moving through a grid line. The fluid, the flow is moving through a grid line. Even though the state itself ideally is not changing, it's the representation of that state that changes. And so to diagnose, here's putting my analysis hat on. If I want to diagnose the full advection operator acting on a tracer, I would have to include that regrid, that remap step, okay? And it's written here in equation 11 as just remapping. It's a word. You can't really write down a clean operator form of it other than just putting something like vertical advection, but it's in quotes. Okay, sorry, I've got some Slack people making noise here. And likewise, it's interesting to note that there is no CFL associated with vertical remapping. Okay, so that's very useful for fine vertical grid spacing. But of course, remember, stability does not imply accuracy. But even having said that, that is really the piece of technology that allows us, if we write our numerics allowing for remapping over one grid cell in the vertical, which we have in MOM6, it allows us to have vanishing layers, allows us to have ice shelves that move the grounding line interactively every time step. And it's a pretty powerful thing. Biting the bullet and going Lagrangian in the vertical allows you to have some real power beyond just the fully Eulerian approach or the quasi-Eulerian or the non-remapping approach. You can, having said that, you can do the vanishing layer problem effectively in the other approaches, but coming at this from an isopycnal approach where you always had to solve the vanishing layer problem gives us a little step up on that problem. So the coastal estuary problem where you have wetting and drying is something that is well handled in the MOM6 context because we do that. The numerics built in the vanishing layers from the beginning. Basically, that goes back to Hallberg's thesis in the mid-90s. Next slide. So I've gone for about 25 minutes. I think I'd like to spend a couple of minutes on just showing a few numerical equations here. And I'm going to talk through this pretty quickly. And if there's any questions, you can come back if you need to follow up on anything. The way that we can sort of characterize from a numerical perspective the different algorithms, it's just by looking at the thickness equation and the thickness weighted tracer equation. So forget the dynamics, just allow the dynamics to be given to us from somewhere, okay? And there are three methods that the community has developed. And we have this quasi-Eulerian, which is what we do in MIT GCM, MOM5, NEMO. And then the vertical AO without remapping is NEMO Z tilde and impasse O. And the vertical Lagrangian remapping is high common MOM6. So here is the thickness equation and the thickness weighted tracer, and the W sigma dot is what we call the diasurface velocity. It's the vertical velocity in the sigma coordinates, the generalized vertical coordinates. And the first term on the right-hand sides of both equation 12a and 12b is the horizontal advection, the convergence of the advection within this generalized vertical layer, sigma. Okay, so next picture, next slide. Because of time, let me just really be quick on this. So the quasi-Eulerian approach, you have a vertical grid change due to step number one. And in this case, it's just due to, say, the evolution of the free surface, okay, like we have in a Z star or a sigma coordinate, terrain following coordinate model. And then we diagnose the diasurface transformation just by the continuity equation. And then we update the grid itself, or the grid thickness, and we can do that in two different steps if we wish to. We can do it in a horizontal and vertical separately. And then that just gives us our updated thickness weighted concentration in equation 6. So next slide. The impasse O and NEMO Z tilde approach is identical to the previous, but the only thing that changes is the specification of the grid. And in this context, there's a target grid and that gives you this evolution of the grid in equation 1. So it's a more general layer motion that allows for to be less constrained in your vertical coordinate choice. Next slide. So the vertical Lagrangian Eulerian is slightly different, although we're trying to write the algorithms in a way numerically that corresponds very closely to the previous two. The first step is evolving the grid according to just the horizontal evolution of the horizontal convergence of the thickness weighted velocity. So it's layer motion via horizontal advection. And then there's a calculation of the diasurface transport, and it's 0 by definition in the first step, okay? So there's no transfer across the layer because it's a fully Lagrangian step. Again, remember the mantra that advection is motion relative to a grid. If the first part of the algorithm is Lagrangian, there is no advection in the vertical, okay? Of course, there's horizontal advection. And so we update the thickness based on a purely adiabatic horizontal advection step, the horizontal advective thickness update. That's step number 3. And likewise, we update the thickness weighted tracer concentration within layer according to that horizontal convergence of thickness weighted tracer concentration. And then step number 5, we update the thickness of a cell according to the target layer. And that is the regrid step. And we have some specified target grid. In the example that I showed, that was our isopycnal. That was our Z coordinate, our geopotential. And from that, we can diagnose the motion of the grid itself relative to the fluid, the W sigma dot, and that's the target minus the H dagger divided by delta time. And we can then use that to regrid the tracer. And that's the vertical Lagrangian approach in MOM6 in a nutshell. I have no diapycnal stuff going on here. I don't have any diffusion. The diffusion, in fact, is added in the step, if you had tracer diffusion, that's added in step number 4, okay? So we have everything going on in step number 4 in the trace equation except W sigma dot is 0, okay? So don't confuse Lagrangian for adiabatic. We still have diapycnal velocities, we still have diffusion going on in step number 4, okay? We just don't have the W sigma dot. W sigma dot is 0. It's a grid motion is 0 in that Lagrangian step. Vertical grid motion is 0. That may be a bit much. We can come back to that if there's any questions. Next slide. Another point that I want to make is about Jet-McWilliams. Where does that live in this formulation, in particular the vertical piece of Jet-McWilliams, or eddy advection, whatever it is, either Fox-Kemper et al. Or Jet-McWilliams. The scalar equation without remapping, and this is a sort of fish-like generalized vertical coordinate layer here. It's not kidney bean, this is fish bean. So we've got, just remember you have a U star, V star, and W star, where the star is your eddy-induced velocity. And as you see here, we add that W star to the diasurface transport in a model without remapping. Okay, so ignore the equations below, but just briefly, it's the full, like we do in Z coordinate models. Now go to the next slide. In the layered approach, in the vertical Lagrangian remapping approach, we don't do GM as GM95. We do GM as a layered model would do GM. We interpret the parameterized eddy-induced velocity as a bolus velocity. It's just horizontal advection within layers, okay? So it's a U dagger equals U plus U bolus, where that U dagger, I should have probably used a different symbol. That's the residual mean velocity. And the transport across the layer is just due to the layer motion itself, W sigma dot. Okay, so that is an important realization when you're thinking about implementing Jet-McWilliams, which we've done in MOM6, but it is something that's distinct. We're thinking about it in a layered model, like an isopycnal layered approach, not a Z model approach. I think that's it. If we keep going, I think that sort of closing comments. So this is from Alistair's et al. Paper, and many of you have seen this. This is more a importance of hybrid, or the potential importance of hybrid, at least insofar as what we've done in our quarter degree no man's land climate model. No man's land in the sense of quarter degree is an awkward resolution to be running climate models, but we think that it's a useful resolution for us. The top figure here is the drift in the horizontally average temperature over 5 cycles of core 4 simulation. When we run with hybrid, which is Z star in the upper ocean and isopycnal in the interior. And the second figure on the right is the pure Z star, and we get a lot more heat uptake. And the figure on the lower left is the global average temperature. And the red line that jumps off, that climbs to a very large number, is the Z star simulation. Next slide. I think that's so. The solution that we have in MOM6 for vertical coordinates is very general. I think that the cutting edge research numerically is in finding the best vertical coordinates. There's still we don't claim that we have the best vertical coordinate with the HICOM-like vertical coordinate with the Z star going to isopycnal. There are lots of issues that we have found with that in the high latitudes in particular. So we're not there yet, but we do think we have a framework in the vertical Lagrangian approach that allows for us to explore that problem in a very, very rigorous way, in a robust way. Allows us to solve the wetting and drying problem very robustly, to remove the vertical CFL condition, which again, the CFL condition can be removed in other contexts in Eulerian models, but it's fairly natural in a model that was started out as an isopycnal model, because you had to solve that problem with vanishing layers to begin with. Next slide. That's it. Thank you.
Thanks, Steve. I think we can take a few minutes for questions here. Let me see if I can make this work. And maybe if Todd or Elizabeth, I'm not apparently.
I can see hands from Gustavo, from Peter.
I know, but I can't unmute them.
I can unmute myself.
Okay, go for it.
Steve, what do you think is the right way of computing vertical velocity within the MOM6 framework?
Yeah, so if you want to diagnose like geopotential vertical velocity, is that the question?
Yeah.
Yeah, so we thought we had it a few years ago when Andrew Shao was at JFTL. We said, oh, we can just do it offline. We can do it in Python. We can make everything sort of just take the convergence of the horizontal transport. But we forgot that there's a time derivative of the coordinate moving itself. I think you need to probably do it online. And it's a piece of code that we're hoping that you'll produce. It's something that needs to be done for certain diagnostic purposes. Say you want to, if you want to continue doing Lagrangian particle trajectories with UV and W, for example, you'll need to have W. So we know how not to do it. It's just a matter, and I think we know how to do it. It's just a matter of getting the code in together and doing it.
Okay. Alistair, did you have a point to make?
No, I was clapping.
Oh, okay. 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 Anyone else? Any other questions?
So Steve, how do you decide when and how frequently to do the vertical remapping?
Yeah, it's a good question. I think Alistair, hopefully you can correct me. I think we do it every 4 time steps. Is that right, Alistair?
Yes. Yes.
And is that 4 tracer time steps or 4 dynamic time steps?
It's 4 dynamic time steps once. We're doing, well, it varies on the configuration and resolution, of course, but we're currently doing it every tracer time step, which is generally 4 dynamic time steps or more.
And so the decision to do it that way is, I guess, based on empirical, and you try to reduce the amount of remapping to the minimal amount that you can. Is there anything more objective than that, Alistair? Yeah, so he's moving away. I had the same question asked at me. Alistair, is there anything objective with the number of regridding time steps, remapping time steps?
So I think there's an accuracy issue. You obviously, if you don't remap regularly, you're distorting the resolution as you move forward. I think it's one of those things where there's some empiricism involved. It would be useful for someone to one day do a systematic study of what the best ratio is for particular resolutions and processes. It's something that perhaps everyone should do.
I mean, I think that one, how the upper limit on how long you can do it is you don't want the interfaces to tangle, right? That is definitely probably too long.
Yeah, so more turbulent the flow, you need to be sure that you're remapping enough. But of course, your time steps itself will be smaller too. So it's an interesting sort of numerical research question to determine that optimal, if there is an optimal.
Luann, you had a question? You can go ahead and unmute yourself.
Yeah, I was wondering, I remember when we were playing around with the mix layer for him way back when. So is there, and I might have missed it, is there something different you do in the surface layer, or is it?
It's a continuous vertical coordinate, just like HICOM. And so we have options for KPP. We have
Okay.
energy-based approach that Reichel and Hallberg have. So we have CV mix in there, and we've used CV mix with KPP. I know that's what NCAR is using. So there's no more bulk mix layer when you do the continuous vertical coordinate. We still have an option in MOM6 to do the discrete vertical coordinate, the discrete isopycnal coordinate, as a gold simulation did, and there's still a bulk mix layer option if you really want to go there.
Okay, thanks.
Okay, I think we'll move on to Alistair. If there are more, oh, there was another question. Joning, go ahead and unmute yourself. Yeah.
Hi. Okay, thanks for the talk. I was just curious about the very last slide on the effect of the vertical coordinates on ocean heat uptake. Maybe I missed it, but what was the major difference between the two vertical coordinates that you showed?
The one where you got a lot of heat uptake was a very much like a geopotential. It was what we call Z star or Z star in American parlance. And the other one was like what we call the HICOM vertical coordinate, where the interior is very isopycnal-like, and the upper ocean in the boundary layer is more Z star-like. So we reduced the amount of need to we still remap the same amount, but the amount of remapping itself is much less in the interior when you're kind of following the flow itself with an isopycnal-like coordinate. So that's the only difference. Everything else is the same. The forcing protocol is the same. The physical parameterizations are the same.
Okay, so that's saying that we need the enough amount of remapping to in order not to.
Well, again, just to be sure we understand, both of those models use the same vertical Lagrangian remapping algorithm. Mm-hmm. It's just the choice of vertical coordinate within that algorithm that differs.
Okay.
Okay. One of them is 100% Z star, and the other one is a hybrid, Z star isopycnal. Okay.
Okay.
And so yeah.
Cool. Thank you.
Okay. Alper, go ahead and unmute yourself.
So I'm wondering if the regridding could be made adaptive, similar to adaptive mesh refinement, where you can apply regridding based on some automated quality measure. And then that would probably also allow you to apply regridding locally, both temporally and spatially. Would that be possible?
Yeah, I see Alistair shaking his head. I think that's a nice idea. Yeah. Sounds like a great project.
So, well, if I can just follow up. So there was a student of Andy Hogg's, Angus Gibson, who actually did an adaptive isopycnal approach, which is trying to optimize where to put surfaces to try and track neutral surfaces. And then Hans Bouchard has similar sort of ideas going on for coastal modeling. So, I mean, it is very much the sort of thing you can do. There's no restrictions on what the coordinate system you can use. So adaptive is a good idea.
I think one of what Rainer Bleck likes to use, I think he coined the term coordinate free. I mean, you just need an algorithm to tell you what your coordinate surface is, and then you remap to it. And that algorithm doesn't need to be written down in a form of a PDE. It's just some algorithm.
Okay. Luann, did you have a follow-up? I see your hand still up.